So when we define a state, what we can do is we can plot it. So since I need two variables or one variable, whatever it is, uh, I can plot pressure, volume, temperature. Those are the three natural state variables that I can easily measure for a system. And I get this beautiful 3D plot, but it's difficult to use. Okay. And then I'll discuss some of these critical points and et cetera in a second, but you can see basically you have areas on this plot, which we will never use this 3D plot. I just want to show it to you for what it looks like. There are areas where you have one phase, like the solid here, or the liquid here, the gas here. And there are areas where you can have two phases coexisting here. Or you can have a triple point, we have three of them. Those kind of by and large what's happening here. And basically, as you can see, that the pressure is going up as you go up the vertical axis, and the volume goes up as you go across the horizontal, and temperature goes up as you go into depth-wise. And what we should do is basically look at 2D projections, and we will really look at two and really need one for this class. So in Gen Chem, you remember, we talk about pressure versus temperature a lot over there because it's a very visual way of representing phases. It's not a very practical phase diagram from the point of view of analysis and mathematics, but it does give you information regarding when you have a solid, when you have a vapor, when you have a liquid. A liquid, when a liquid and a gas kind of have blurred lines where there's a point wherein a liquid can no longer exist and a gas can no longer exist, and beyond which we call that the supercritical area, and that corresponds here to that little point here, which I have denote here as C is the critical point. So any temperature above the critical point will have above the critical pressure will have a supercritical fluid. Supercritical fluid, you can think of it as quote unquote another phase, but it's basically an indistinguishable fluid that has some liquid-like and some gas-like properties. So we will discuss that also, supercritical fluid as well. You have pure liquid and pure gas and pure solid represented here directly. And these lines here, the black lines here, correspond to transition, the transition zones. So basically, from the point here, the pinch point, which is the triple point, to point C, okay, this line here corresponds to the vapor-liquid equilibrium. So if you define a state anywhere here on this line, that means that both the liquid and the gas will coexist. Okay, so as we discussed a few minutes ago, if I have a boiling cup of water, I have both the steam and liquid water coexisting. And that's when we have two phases, one component. And so during that transition, okay, what we could impose and what we see is that the temperature and the pressure remain constant during that transition. The temperature will remain constant as you add heat. And if you remember from general chemistry and also from physics, the idea of latent heat was embedded in there, meaning that if you introduce heat to the system, it will not be represented in terms of increased temperature. It will only be represented in addition of heat, which we call latent heat, latent meaning hidden. Again, this line here represents the solid-liquid equilibrium. So on this line, you have both solid and liquid, and here you have both solid and gas. Okay. As I mentioned, these are not very useful to us because they're not very conducive to quantitative treatment. But if I look at, let's say, so if I project this thing on the PV rather than PT, then I get something a little more interesting, and that's the PV diagram, which we will use significantly more. We will not use the actual diagram, but we have tables in the back of the book, and I'll show it to you. Specifically, what we will use is this dome in here, as well as the liquid phase and the vapor phase. We won't really deal with solids in this class, but just to show you, basically this purple dome here is basically a 2D resolution resolving of this line. We have both liquid and vapor. So to the left of this dome is the liquid region, which is just this. To the right of this dome is just superheated vapor, meaning, oops, it's just this, okay? And within that dome is that line. So it's nice because I'm able to resolve this and understand what happens during the transition. So again, to remind you, when I have a transition between a liquid and a gas, okay? So the temperature will stay the same during that transition. So these dotted lines, even though temperature is not directly represented in this chart, these dotted lines are known as isotherms, meaning the temperature remains constant. So let's say I follow some temperature, I don't know, like 25 C or something. And I go down this, at 25 C, I want to see what happens. So it's always going to be 25 C along this line, okay? And I want to know what happens at 25 C as I change the volume and the pressure. So you can see at 25 C, and I'm not changing the temperature at all, as I'm reducing the pressure on my liquid, I will get to a point where it will start boiling. Why? Because you're pushing down on the liquid. And all of a sudden, the weight on the liquid that you're pushing down with is being reduced enough that the liquid can start evaporating. And it's doing so here at a constant pressure and constant temperature until it reaches a point where the entirety of it evaporates. And now I only have vapor. And again, I'm removing that weight from above that vapor. And you can see the temperature stays the same, but the pressure will continue reducing because I'm removing that weight. Okay. During this transition, I start out with 100% liquid and I end up with 100% vapor. And between the 0% vapor to 100% vapor transition, as I'm going across to the right, the amount of vapor increases, the amount of liquid decreases. Once I reach 100%, then the pressure is allowed to then modulate itself again and no longer stay constant. But during this transition, I have PT constant. Okay, and obviously the volume will change, density will change. So what we will play a lot with this. I just added these areas here to show you that the entire thing, the entire diagram translates to this. But if you look at your book, these light pink lines, the triple point line, the solid liquid, the solid vapor, the solid area, they don't even talk about that. They don't even show it on the plot, but it is there. As a matter of fact, I truncated it. I think this goes all the way up. This goes all the way up. But we will not be dealing with solid, liquid, and solid vapor. So don't even worry about that. We will just be dealing with these three states. Okay. And I'm not showing you the TB diagram, but you can look it up yourself. The TB diagram looks very, very similar. And what they do with TB is basically replace this P with a T, and you still have a dome, and it just looks a little bit different. And instead of having lines of constant temperature, you have lines of constant pressure. That's very, very, very similar in analysis. Okay. And so within that wet dome, as I mentioned, I start out with 100% liquid here, and I go to 100% gas. And as I'm changing the volume of this thing, the amount of gas will increase at the expense of the amount of fluid. Okay. So depending on where I am in what we call this saturated liquid vapor region, I can determine what percent of my mixture of liquid and gas will be gas and what percent will be liquid. And I'll show it to you in examples in a second, but it's going to be very important to understand how much of my mixture is liquid and how much of my mixture is gas. And you might imagine it's important because in understanding how much vapor you have here, you can understand the beginning and end state, right? So even if even if the states that you're dealing with, your process starts here and ends here, you can still have some energy transfer from here to here, even though it's all within this dome, because the volume will change. So even though the pressure and temperature won't, the volume will change, which means, for example, the expansion work will change, right? Work is equal to P dV. So the volume will change. I'll have some change in work, and so change in energy, and so change in my system. So it is very important to understand specifically where you are on that dotted line. And so we've developed this thing called the quality, which we will denote with the letter X. And so if I have some random point Y, I want to know what percent of Y is liquid and what percent of Y is gas, I can use this relation. So for Y, which I don't know Y. I do know Y for the liquid, which conveniently they subscript with F. And then the Y for the gas is G. These things I can look up at a table, and I'll show you in a few minutes how to do so. This I can't, because it just depends on where I am. So if I want to know at point Y what percent is gas, I will just use these tabulated values, and I'll find it. And so I could say, like, it looks from this particular diagram that it's about 50%. So if I were to use this particular value here, probably I'll get 0.5 or around 0.5 based on this picture. And of course, it may be somewhere else. And it may be directly here, in which case X will be 0. It may be directly here, in which case X will be 1. And so anywhere in between. So it's a fraction, it's not a percent, but same idea. Okay, so if I told you 100% quality, I meant X is equal to 1, and I mean the whole thing is gas. Okay, so we will use that, and we will discuss this. Okay, so we have these reference tables at the end of the book, which you will use extensively. And I will show you how to use that in examples and here as well. So instead of having these big charts for different compounds, which you could do, you could look them up, not a big deal. The book was able to compile tables for you, which I think is better. I think that's why they do it, because you can have a wider range of pressures and temperatures, for one, and two, it makes for much easier reading rather than having to pinpoint a point on the chart and guessing what that is. Okay, and these are the tables that they have. They have water, and they give you the saturated water table, the compressed liquid water water table, and the superheated steam water table. So again, they give you tables corresponding to compressed water. So you can look up if you know you're only in the liquid region and there's no gas, there's no saturated gas at all. You can find out where you are here somewhere. They give you the superheated vapor or superheated steam for water, and they give you the saturated. What happens if I have both liquid and gas at the same time? And I'll show you an example, a few examples of that. In thermal, we will use a bunch of refrigerants. So they also give you refrigerant data tables for refrigerant 134A and 22. They don't give you the liquid, but they give you the saturated and superheated, meaning, again, they give you this region and this region for the refrigerants. And same thing for ammonia and propane. Okay, we have a set in the back of the book in SI units, okay, which I believe are in red color, and the tables that are blue color are in the customary system in the U.S. imperial system. Okay, and we can use these tables to find temperature, pressure, specific volume, a specific internal energy, specific enthalpy and entropy, which we'll discuss later. H and S we'll discuss later, but we can find TP, V, and U directly from those charts. And again, we will need one or two depending on where we are. So let's look at an example quick, and then we'll do another one on the board in a second. So how do I know which table to use? Okay, so let's say the question says, here's the question: a water substance at 3 bar with specific volume of 0.25 meters cubed per kilogram. Okay, and I want to know what the temperature is. Okay, so I have 3 options for water, as I just mentioned here. So I go to the back of the book and I see I have a saturated table, I have a liquid table, and I have a steam table. Meaning, again, I have here, I have here, and I have here. So I was given a volume somewhere here, and I was given a pressure somewhere here. and I want to know what the temperature is. Okay, seems reasonable enough. So again, I could probably use a version of this, but you can see how much of a pain it would be to figure that out from the chart, from the chart. So using the table is much easier to do that. But I just need to know which one to use. Do I use the liquid one? Am I here or am I here? Okay, not so hard to figure that out. Let me show you. So I know that the pressure is 3 bar. Okay, so I have the saturated water, which is that dome. I have the vapor, which is to the right of the dome, and I have the liquid, which is to the left of the dome. So right away, if I go to the liquid, the lowest pressure for that table for water is 25, and we're at 3. So I can discount table A5 directly. So I don't need that because I'm not anywhere near 25, so the heck with that. So I'm not going to go there. Okay, so now I have to contend with between table A3 and A4. Again, the dome. Am I a dome or am I a vapor? Okay, so I know I have 3 bars. So I go to the table here, and you can see that the pressures, I cut it to get to 3. So here I'm at 3 bar. And they show me that the liquid has a volume of 1.0732 divided by 1,000. That means that you take this value here, this 10 to the third, and divide by 1,000. So it's like 0.00 whatever, 1. And here, I have the volume for the gas being 0.6. Okay, 0.6058. For the 3 bar over here, I could see I start out at 0.606, which makes sense. And then I just increase a whole bunch until I get to 1.341. Okay, so what that means, since my volume is 0.25, it's below the blue. So I shouldn't use A4. I should use A3. Okay, so that's how I figured that out. So I know I'm between this and this. So basically, you find your V and you find whether you're between these 2 values. If you are, use this table. If you're above that, use this table. If you're below that, use this table. That's pretty much how you do that. So I know I'm somewhere in between these 2, so it doesn't, I didn't ask you yet what to do with it. But if I know I'm somewhere in between this at 3 bar, that means that the temperature for my system is 133.6 degrees Celsius. So that's basically the answer. I just asked the temperature. That's how you get a temperature. The temperature is 133.6. And I don't know how I got that line. Okay, so let's find other properties. Okay, so let's say the same question. I have a water substance at 3 bar with this specific volume, and I want to know the specific internal energy. Okay, so I already determined that I got to use table A3, right? Because that's what we want to use. So what do I do? I want to find the U here. And I know that my volume is 0.25. And again, this is not 1.732, it's 0.00100732. It's divided by 1,000. It's this number that over 1,000. So I'm starting with a really small number and I'm going all the way to 0.6. Okay. So if I told you, if I in the question said that the volume was 0.6058, okay, that would mean that even though I'm saturated, all of it is a gas. So going back to that chart here, I know we're somewhere here. Yeah, we don't know where we are. This corresponded to a really, really small value, 0.001, whatever it was. And this corresponds to 0.6058. Okay, so if I told you I have 0.6058, that means all of it is a gas. 99.9% or 100% gas. If I told you it was 0.001, whatever that was, that would be 100% liquid. I'm somewhere in between. So I have to figure out what percent gas and what percent liquid I am. And then I can determine the U. So it's a very systematic way of doing it. Let me show you. So first, you want to find the quality from whatever I gave you. So I gave you the V. So find the volume. You have these 2 numbers to figure out find the quality. You have these 2 volume values. You can get the quality. Once I find the quality, I'll apply that to the internal energy. So wherever the distance between this and this is relatively, it will be the same thing between this and this. So again, if I give you V is 0.6058, that means it's 100% vapor. If it's 100% vapor, direct I can say that the internal energy of that system is this, because this corresponds to 100% vapor. If I told you that the specific volume was this, that means that the internal energy would be this. But because it's somewhere in the middle, whatever distance between these two it is, the same thing here on a relative scale. So let's do that. So again, the quality is whatever the specific point I want, okay, minus the property for the liquid, divided by the property for the gas minus the property for the liquid. Okay, so y is just a random thing. I could put v for it, I could put u for it, I could put h for it. So since I'm given v, let's put v. So I want to know for my v, and my v here is given as 0.25, okay, what my quality is. So I'll put 0.25 for my v, and I know that the volume for the liquid is 1.07325 by 1,000. Again, this means divide that by 1,000. It is not here, so don't divide by 1,000. It is here. So it's 0.25 minus the volume of the liquid divided by the difference between the gas and the liquid. So I put that in, and I say that, okay, so that means I have, oh, this is a typo, I should say it too. 41.2% of my mixture is vapor. That's what that means. Okay, so I can use the fact that I have 41.2% vapor, apply that here and find the internal energy. So let's do that. Okay, so with 0.412, I will use that with U. Okay, so again, the quality corresponds to any property, not just volume. So I could put that with respect to my U. Okay, and I know the U for the liquid is 561.15 here, and I know that the U for the gas is 2,543.6 from right over here. Okay, so I'm going to put them in, and I'm going to solve for that U, knowing that X is 0.412. So then I find that U is 1377.9, and I'm using the units that they have here. It would be kilojoules per kilogram. So let's do some examples. Before I do it, let me just give you the algorithm. I'm going to give you some extensive property, Y. So it could be V, right? It could be like this V here. Make it let's truncate a version of it tonight. Yeah, I could be V, it could be U, it could be H, or it could be S. Any of those values, I can give you any of those 4 values. And we're not dealing with S yet, so don't worry about it, but we will eventually. So based on one of those values, if it falls between the liquid and the gas in the saturated table, use it. If it's bigger than that, use the gas. If it's smaller than that, use the liquid. Okay. If it is in a saturated table, find the quality, and then you're able to find other properties. Okay. Otherwise, you have to find Y or whatever that thing in the other 2 tables, and you may need to interpolate. So before I do another example, let me show you interpolation. And that's going to be fairly quick. So let's say I have this table here, and I need to know the property at 143 degrees Celsius. Okay, so I'm not given that directly in the table. Okay, so I know I need this table. I figured out I need this table, and I want to find the specific internal energy U at 143. So I'm given 120 and I'm given 160. What the heck do I do? So basically, I'm doing like a weighted average type thing to figure that out. Rather than kind of riffing with it, I'll give you the equation. But that's basically what we do. We know this. We know this. We will construct a straight line between them using the point slope formula and figure out based on 143 what the U should be. Okay, so the value at 143 is not given, but we do know that we have the U at 120 and the U at 160. So we're going to do interpolation. And this is the equation for interpolation, which again is just a point slope formula. So the value that I want at Y3, so in this case at 143, I want the value at 143. I'm going to subtract the closest value below, which is going to be at Y1, which in this case would be 120. And then I'm going to divide that by the the closest value above, which is at 160, minus the closest value below, which is at 120. Okay, and then I'm going to equate that to y3, which I know is 143 degrees Celsius. Y1 is 120, and then 160, 120. That's basically what we'll do. And this is going to work with any two properties that you'll be given. And we will do a bunch of examples, and I'll show you. But that's basically sort of the idea. Okay, so I know that I want this thing, u at t is equal to 143. So again, that corresponds to the equation right here before, the value I desire right here. And then I subtract the one below, and then I use the value above and the value below to cap that. So those are here. And then I use the temperature to for the other side. So I'm looking for the stuff at 143. I know where I'm looking at. I need the 143. I just don't know the u there. And when I do this treatment to it, I find that u at 143 is 2,578.1 kilojoules per kilograms. And again, I'm basically constructing a straight line. So if I asked you specifically for 140, you can go through all this rigmarole, or you can just take the average because you know it's going to be right in the middle. It's going to give you that too. But this is not directly 140. It's going to be something a little more inconvenient, so you're going to have to use this relation. So I suggest kind of writing these two things down. This one to find values that are not directly on the table, and the quality, which this thing, to find anything for the saturated water, saturated anything, when you have a mixture of gases and liquids. You will need those two a lot for these tables. So with that, let's do some examples.